Alright guys, so this is our second video for our flipped classroom lesson on higher degree polynomials. And in this video we are going to talk about the fundamental theorem of algebra. The fundamental theorem of algebra states that the degree of a polynomial corresponds to the number of linear factors that we multiply to get that polynomial, which corresponds to the number of zeros that that polynomial will generate, whether those zeros be real or imaginary. Right? So right off the bat, we've got f of x equals x cubed minus x squared minus 6x. And what I want you guys to do is to factor this out to show that our third degree polynomial is going to generate 3 linear factors. All right, so pause the video and give this one a shot. All right, guys, so right here we can immediately factor out an x, and then from there we can factor our quadratic into the linear factors x minus 3 times x plus 2. Now clearly right here we've got 3 linear factors, which corresponds to our degree of 3. And if we think about it, it should make some sense. Right here, if we are multiplying 3 linear factors, right, then the highest power term is going to come from the multiplication of all of the x's, right? We multiply maybe these 2 linear factors together and we get the quadratic, and then when we multiply that x through, the highest power is going to be our cube, right? So 3 linear factors are going to have 3 x terms in them, and when we multiply all of those linear factors together, in the end, we're going to get the highest power term from multiplying those 3 x's, giving us a cube, right? So pretty logical when we break it down. What we want to show now is that those linear factors are going to correspond to zeros. When we're talking about the zeros of a function, really we're talking about x values that give 0 function values. And so right here, remember that the function values are the y values of the function. So really what we're looking for are the x values that will give us 0 y values. In the end, what we're going to see is some graphical correlation here between x values that make f of x equal 0 and graphically the x-intercepts of the graph of the function. Right here, if we are solving for our zeros, we can set the equation that defines our function equal to 0. And then, of course, we would find our zeros by setting each of these linear factors equal to 0. So x equals 0 is going to be 1, 0. We'll get a 0 from setting x minus 3 equal to 0, and we'll get a 0 from setting x plus 2 equal to 0. Right here we can say another 0 is going to be x equals 3, and our last 0 is going to be x equals 2. So the 3 zeros that come from our 3 linear factors are x equals 0, x equals 3, and x equals negative 2. And right here, what we can say is, if we are looking at the x values that give us 0 function values, those are really where y equals 0 and y equals 0 when we're on the x-axis. So right here, when we are looking at the graph of this function, the zeros of the function, of course, correspond to the x-intercepts, right? So right here what we can say is the zeros, or the roots of our function, and the x-intercepts are really all the same thing. We can say so long as the zeros are real. Meaning so long that those zeros are real numbers, right? If we look at the quadratic, x squared minus 2x plus 5, what we can see here is a parabola that isn't crossing the x-axis, right? So right here, looking at this guy, immediately we can't find the zeros because we can't factor them, right? One way we might think about this is, what multiplies to give us 5, adds to give us 2, and of course there's nothing that can multiply to give us 5 and add to give us 2, and that's one way we can see that we can't factor this. So right here what we can do is find those zeros with the quadratic formula. So the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So right here, we basically would say we're taking a, b, and c from standard form of the quadratic. So right here that would be ax squared plus bx plus c. We can say our a term is going to be 1, our b term is going to be -2, and our c term is going to be 5. Right here, what I want you guys to do is to go ahead and find the zeros of this quadratic using the quadratic formula. All right, so we can plug our a, b, and c value into the quadratic formula, and we're going to get -2 plus or minus the square root of -2 squared minus 4 times 1 times 5 all over 2 times 1. Now, when I am evaluating my quadratic formula, I always plug everything in and then I evaluate these 4 numbers and then I combine them. So right here, what we can say then is we would have x equals 2 plus or minus the square root of 4, and then 4 times 1 times 5 is going to be minus 20 all over 2. Bring our square root in a little bit. Now right here, basically, we can say that x equals 2 plus or minus the square root of -16 over 2. And right here, that is going to give us 2 plus or minus the square root of -1 times the square root of 16 over 2. And finally, right here, we would get x equals 2 plus, and then right here we could say this is 4i over 2, which simplifies to x equals 1 plus 2i. And right here, we would also have x equals, and then this is going to be 2 minus 4i over 2, which we would simplify to x equals 1 minus 2i. Now, these are imaginary numbers, right? And imaginary numbers have no place on a number line, specifically the x-axis, right? So basically right here what we're saying is our zeros are imaginary. Now, even though our zeros are imaginary, we can still represent our quadratic with 2 linear factors. And those 2 linear factors would basically be right here, f of x equals x, and then minus this 0, so minus, and then 1 plus 2i. And then the other linear factor would be x minus our second 0, and that would be minus and 1 minus 2i, like that. And we could even simplify a little bit. We could say this is f of x equals x, and then right here minus 1 minus 2i, and then x, and then minus 1 plus 2. So right here, that fundamental theorem of algebra holds true, right? The degree corresponds to the number of linear factors, which corresponds to the number of zeros, whether they be real or imaginary, right? And we have imaginary numbers in our linear factors as well, but we still have 2. All right, so this is going to be the end of this video. We will come back and talk about multiplicity of zeros in the next video. See you guys.